So this first unit is kind of going to be a high-level summary of the different modes of heat transfer and some governing equations that we will use for all three. And we already defined the three modes of heat transfer in the very beginning of class, many moons ago. And so we essentially have three different modes of heat transfer: conduction, convection, and radiation. So just to define these a bit more, and kind of again, because I think we sort of already talked on these points a little bit earlier in the class. But conduction is heat transfer in a solid or a stationary fluid. And remember that a fluid can be a liquid or a gas. And so this is heat transfer that occurs from a point at a higher temperature to an adjacent point at a lower temperature. And conduction occurs due to the random motion of the material's constituent atoms, molecules, or electrons, which is another way of saying it's diffusion. Okay, so this represents the transfer of energy from a more energetic state to a more energetic particles, to less energetic particles inside of a substance due to the interactions between particles. Okay. So the key takeaway is conduction happens in a stationary material. So all solids are going to be stationary. The molecules are all stationary relative to other molecules in that material. And it can also happen in fluids. So a liquid or a gas, the molecules be relatively stationary to one another if they're not moving, right? But liquids and gases are capable of moving. So that's why we have to talk about another mode of heat transfer, which is convection. So convection is energy transfer between a solid surface and an adjacent moving fluid when they're at different temperatures. Okay, so convection actually involves the combined effects of both conduction or diffusion and advection. So advection is essentially temperature or heat is going to be carried because of the nature of the fluid moving. So this is due to motion. Okay. There's two types of convection. So forced convection is flow caused by external means. So these are things like fans or pumps or even the wind. So there's some external factor that is causing the flow to move for forced convection. For natural convection, sometimes that's called free convection. This is flow induced by buoyancy. Forces, never mind, just buoyancy. Forces which arise from density differences caused by temperature variations in the fluid. So if, I think I mentioned this earlier in the semester, but if anybody's ever noticed, like if you look over asphalt in the summertime, you can kind of see like a mirage-y sort of thing. So that's essentially free convection. So the movement of the fluid in that case is because the air that's very close to the hot pavement is being heated up. It becomes less dense and that makes it more buoyant and it wants to rise above the cooler air on top, which will flow down. It's very cool. I could talk about that for a long time. Okay, which I will in 3500 if you visit me there. The third form of heat transfer is radiation. So radiation is the transfer of thermal energy by electromagnetic waves. In a particular wavelength from a point at a higher temperature to a distant point at a lower temperature. This represents energy that is emitted by matter due to changes in electron configurations of its atoms or molecules, and it's transported as electromagnetic waves. Or photons. Radiation is most efficient in a vacuum. And what that means is that it does not require the presence of a medium for transport. So that's really one of the key differences between conduction, convection, and radiation. Both conduction and convection require matter to be there to do it. Radiation does not. Okay, so this is the high level summary of our three different types of modes for heat transfer. And next we're going to go over kind of a high level discussion of each of them, including some equations. So for conduction in solids, this mode of heat transfer occurs due to energy transfer in the molecules. In stationary gases and liquids, energy and temperature are related to random translation, rotation and vibration of the molecules, which results in collisions between molecules. When those collisions occur, energy is transferred from a higher energy state to a lower energy state or particle. Oh, you know what? This first one, sorry, I got this wrong. I copied down the wrong thing. This is lattice vibrations. Sorry. Okay, so kind of if you look at this, bless you, if you look at this figure over here, so in a solid, if you look at this schematic of how atoms or molecules are arranged in a solid, they're in this very structured, usually crystal type structure. And so energy is going to transfer through just vibrations, but the structure itself stays the same. But for liquids and gases, since they are less organized with one another, then we have more randomness and kind of different modes in which the energy can change. So we're talking about translation, rotation, and vibration of the molecules, not just vibration anymore. Does that make sense? Okay. So Fourier's law is what governs conduction. So if we think of a very simple case where we have a wall of some uniform material and a thickness L and a cross-sectional area A, and then we have two differing temperatures on either side of that wall. Experiments have been done to show that the steady rate of heat transfer, so our heat transfer we know is going to go from hot to cold, so we're going to have Q dot generally going this way, right? And this is happening over this area A. And so we know from experiments that this rate of heat transfer is equal to some parameter K, and this is not the K from the ideal gas stuff that we were just talking about. It's a different one. So K times area times the temperature difference divided by L. Okay, where in this expression, L is the thickness of the material in the direction of heat transfer. All right, A is the, A is our area through which the heat transfer occurs. So this is perpendicular to the direction of heat transfer. So this is our area through which heat transfer occurs. And this is perpendicular to Q dot. Obviously, T1 minus T2 is the temperature difference. And then the most interesting parameter here is K. So like I mentioned, this is not the same K that we were just talking about in thermodynamics, but this is the thermal conductivity. Of the material. It has units of watts per meter Kelvin or similar. And then Q dot is the same as before. So Q dot, let me pick a different color here. Q dot is our rate of heat transfer. So that notation is the same as thermodynamics. Okay, so let's talk a little bit more about our thermal conductivity. So thermal conductivity K can be thought of a measure of the material's ability to transfer thermal energy by conduction. So to what degree does a material allow heat to pass through it? Okay. Generally, K is a function of temperature and sometimes direction. And by direction, I mean the orientation of the material, but this is only for non-isotropic materials. So isotropic materials just mean that the material properties are the same no matter what direction you pass through it. If you have a non-isotropic material, that would mean that its orientation or the direction in which you pass through it will change how the properties are. So an example of a material where this would be the case would be a polymer. So polymers tend to be non-isotropic, they're very directional. So depending on the orientation of your temperature gradient and the material, your thermal conductivity could change. In this class, we're generally going to assume isotropic materials. So, but just to note, that can happen. Okay. The table that I have right here is also in the book. So this is table 16.1 and A23 through A25. All right, so this gives a sense of thermal conductivity for different types of materials. So I'll just zoom in here a little bit more. So lower thermal conductivity is going to be your gases. And then as we move up in thermal conductivity, we're going to pass through things that are insulators, then liquids are slightly better, non-metallic solids. And then as you increase and go to different types of metals and non-metallic crystals, you get better and better and better heat transfer properties, okay? So hopefully this is fairly intuitive just based on your lived experience. So for example, you know, this is why if you have like a double wall insulated coffee tumbler, that's why it has a gas on the inside. They don't allow heat transfer very readily through conduction, okay? Okay, we also have another table in the book I don't remember what number that one is, but this gives the thermal conductivity of several kind of common types of materials. All right, and so again, you'll see that diamond is at the top there, so that has the highest thermal conductivity, and then rigid foam, urethane, and air are the lowest. Okay. Any questions so far? Nothing surprising yet? Okay, great. So if you remember that we talked about how our rate of heat transfer can be written down in this way. So we have our thermal conductivity times area over the length and then times the temperature difference. We can generalize this as the following. So we have our thermal conductivity, and the subscripts denote the direction. So this is assuming that our thermal conductivity could change depending on the direction. So this is a directional thermal conductivity. And then we have our cross-sectional area. So for this one, this is our cross-sectional area perpendicular to the x direction. All right, because we are looking for the rate of heat transfer in the x direction. Okay, and then last but not least, we have our temperature gradient in the x direction. All right, so we can write down three equations like this because we have three directions, x, y, and z. And so just to highlight that, this first equation is all of the x direction stuff. So we see that we have x appearing all in here. So this is because we're looking for rate of heat transfer in the x direction. And so we get our thermal conductivity in the x direction, our cross-sectional area perpendicular to the x direction, and then our temperature gradient in the x direction. So this just repeats itself for the y and z directions. And it also turns out that we can write this as in vector form. So all three of these equations are the same as writing that q dot is equal to minus k a gradient of T. Okay. Okay. You might notice that there is a negative sign on this, right? So the negative sign ensures that the rate of heat transfer is positive in the direction of the decreasing temperature. Oh, I don't have to write temperature twice. Okay. So this helps, this ensures that our equation says that heat is going from hot to cold, not the other way around. Okay. For an isotropic material, which is what we're going to concern ourselves with in this class, that means that Kx equals Ky equals Kz is just K. So that means that we can write that, for example, Q dot X is just K Ax partial T partial X. Q dot Y is K Ay partial T partial Y. And then Q dot Z is KZ. Oh, no, not KZ, sorry. K AZ partial T partial Z. Okay.
So negative.
Oh my gosh. Yes. Thank you. I just harped on about how important that was and then dropped off the minus sign. Classic. Thank you. Okay, and then just one last thing, before we end class here. So if we have a temperature versus position in X, if we have a temperature that starts here and goes down to here, so we have our hotter thing on the left-hand side of this and our cooler thing on the right-hand side, what direction should our heat transfer go, do you think? To the right? Yeah, so our heat transfer should go this way. All right, and so if you notice our gradient, so partial T partial X is negative, right? So we need to add that minus sign to make sure that the Q dot goes to the right. Make sense?